So we covered linear inequalities in the previous section, and now we're going to cover the application of that, which is linear programming. So now effectively what we're doing is we're solving a problem where you have multiple conditions and you want to find the best solution. So with linear equations, there was either one solution, no solution, or infinitely many. With inequalities, instead of it being a single point, potentially, now it could be an entire region. And then with linear programming, we're just taking that idea and just applying it to different scenarios and kind of analyzing like what is the best solution, right? And so it's going to turn out that depending on certain conditions, you can kind of guess what the best solution is going to be. If you don't satisfy certain conditions, then you kind of have like a checklist of things to go through to kind of find the best solution. So we first begin by just defining what it is. So a linear programming problem. And we'll abbreviate it as LP, is trying to maximize or minimize two variables, X and Y usually, but it doesn't have to be X and Y, of the form. So it will almost always be of this form. And so it'll be some equation, P, for profit or whatever you want to say, parameter, really, it's just kind of a parameter, AX plus BY, subjected to constraints like, so your objective, what you're ever trying to maximize or minimize, that typically will be in equal equations because we have a very specific condition that we want to satisfy where the constraints are kind of, well, they don't have to be equations. They could be inequalities themselves. So something like that. And it doesn't have to be strictly less than, it could be greater than. So we can call this like our objective, right? And then if you remember from the previous calculus, we talked about optimization, right? So this is optimization, but with inequalities. Really, that's what it is. It's optimization with inequalities. And before, our constraint was usually limited to one equation. Now it can be as many as we want, right? So you're trying to build a fence around a garden. Your constraint is how much money you have to build the fence. So you're trying to maximize the area, right? There's only one equation for the constraint, and that was how much money you could spend. Now there's many more, right? And so these are your constraints. So the solution to a linear programming problem will depend on whether it is bounded or unbounded. However, it turns out that the solution will usually will end up being a corner point. Okay. We can also call these feasible points, kind of like the feasible region. So something along those lines. And it turns out that if you have a bounded region, so a bounded region, so just to emphasize bounded region, is guaranteed to have an optimal solution. An unbounded region is not guaranteed to have a solution. So that's important. So when you're setting up your linear programming problem and you recognize that you do have a bounded region, then automatically you can kind of get rid of any of the unbounded regions and only focus on the bounded region. If you do not have a bounded region, then any of your unbounded regions can contain the solution. And so that's what you're kind of looking at. But like I said, almost always the solution is going to be some kind of corner point, right? And that's kind of what we're looking for. But here the emphasis is if you have a bounded region, the corner points that create the bounded region, one of those has to be the solution. Whereas if you have unbounded regions, none of those corner points will be the solution if you only have unbounded regions, right? Well, they are not guaranteed to be a solution, right? That's what I meant to say. They still could be a solution. It's just not a guarantee by any means. And just to emphasize that one more time, a corner point will always be a solution in the sense of the solution will never be inside of the region. It'll always lie on the corner. Okay. But not every corner point is an optimal solution. You can have more than one optimal solution. That is possible. But you'll never have to worry about the solution being inside of the region. It's either on the corner or there is none, right? So that's kind of how it ends up working out. So that's the nice thing about these. So let's do our first example. And we're just going to solve a linear programming problem to maximize this function that's given, p equals x plus 2y, and then we're subjected to a bunch of constraints. Now, the key thing here is just being organized. So this is a very methodical process, but the problem is you have to kind of organize your data and information in a way that you can kind of put things together to solve. Because what you're going to end up doing in these problems is you're going to be taking a bunch of equations and setting them equal to each other and solving. And the cool thing is you can actually do this all in your calculator. So if you don't have to show work, you could actually just graph all of these and then find all of their intersection points using the calculator, which I'll show you how to do. And you can get all the answers. Now, if they have to be exact answers, sometimes your calculator doesn't give you exact. But other than that, calculator does these pretty well. So the first step you want to do in these problems is you're going to want to isolate y. So we're still doing that. And the reason we want to isolate y is because it just makes it easier to read these equations to ourselves, right? Because most students have a better interpretation of like y equals mx plus b. It's much more easily visualized when we're graphing. So taking the first equation, we're going to do x plus y is greater than or equal to 4. That's going to become y is greater than or equal to 4 minus x. I just subtracted over the x, right? So I moved it over. And now we have this equation. So, and we can call this equation number 1. And then I just keep doing that for all of them. So then I go to the next one. X plus y is less than or equal to 6. And so I'm going to move the x over. And I get y is less than or equal to 6 minus x. And that should be a 1, not a 2. Like that. And this is equation number 2. And then we go to the next one. X minus y is less than or equal to 4. So then we end up getting, so we're going to move the x over. So we get y, and then we have to divide over this negative right here. So just to kind of emphasize this, that negative right there. We're going to get y is greater than or equal to, and then we get negative 4 plus x, like that. And so that's equation number 3, okay? And if you're not seeing that, I can do it really quickly right here for you. So if you subtract it over, and we get minus x, and then if you divide by negative 1, divide by negative 1, you're going to get y is greater than or equal to negative 4 plus x. So just a reminder, you subtract over, and then if you ever have to multiply or divide by a number, you have to flip the sign. So that's what ends up happening. And so we'll just erase that. and then emphasize that the inequality here flipped. And so we'll go to the next equation. So that will be x minus y. So same thing. We subtract over the x and then divide by -1. So y is less than or equal to, so it's flipping, and then it becomes a +4, and it becomes a positive x like that. And so we get our fourth equation, and now we have them all in terms of y equals. And just to emphasize, the minus sign in front of the y is the reason that this inequality had to flip. So once you have made all of your equations in terms of y equals, now what you want to do is graph all of these. So that's what we're going to do next. We're going to graph. So step 2 is to graph inequalities. And so what's actually kind of interesting about this, and it goes back to what we talked about earlier, you could actually do this problem and find the feasible region by using the interpretation of the inequality and kind of understanding that if it's like greater than, you're shading upwards, and if it's less than, you're shading downwards, and then wherever all of the shading overlaps, that is the feasible region. You can actually do it that way. Just requires a little bit more practice. So equation number 1. So when doing these, make sure to label your axis with the y-intercept. So let me make this actually a little bit better. Like that. So we have a y-intercept of 6, a y-intercept of 4, and a y-intercept of -4, right? The better you draw these, the easier it is to read them and kind of understand what numbers are what. So equation number 1 says, okay, I have a y-intercept of 4 and I have a negative slope. So that means I am going to look like this. So I'm going to go down like this. Doesn't have to be perfect, but the better you draw it, the easier it is to read. And then for the second equation, so I'll put equation number 1, it has a y-intercept of 6. And then it also has a negative slope of -1. So that means they're going to be parallel to each other like that. So we have those two. And then the equation number 3 says, okay, we have a y-intercept of -4. So we'll go to -4. And then I have a slope of +1. So it's going to look like this. Now, this is where if you draw it perfectly, you'll see that -4 and +4, those two equations, they actually intersect each other. So that's good. If you drew it very like sloppily, maybe you missed the intersection at the x-intercept, and it's not as obvious. So sometimes drawing it nicely will help out. And then the fourth equation has a y-intercept of 4, and it has a slope of 1, so it's going to look like this, right? And those are your equations. Now, in this class and in general, when you're dealing with these types of problems, you'd have to ask yourself the following question. Which region is going to be the optimal region, right? So that's what you're going to have to think about next. And you can kind of cheat it. Like I said, if you're doing like a problem in this class or just kind of like these specialized problems, 9 times out of 10, it's going to be the one that is actually like closed, right? Like 9 times out of 10, it'll be the one that's closed. There are problems where it's not, in the sense of the better region might be like this region, but the corner point is still on the closed region. So stuff like that does kind of happen. It's just dependent on the inequalities more than anything. So you can kind of cheat it and know that this is most likely going to be it. Like that's the first one I would look at, right? So we have created and drawn our equations. And now let's just actually do this on the calculator so you can see what that would look like. So if I wanted to graph this on the calculator, you would go to y equals, and you would just plot each one. So 4 minus x. If you have a newer calculator, it will actually color coordinate it for you, which is really nice. So the TI-84CE. That's a nice calculator for this type of problem. It does color coordinate all of them. whereas the old school ones will not. So you kind of have to know which one is which. And then I'll do a zoom 6, and just to kind of get a good picture of what's going on. And so that looks very similar to what we have, right? Some things you can do with the calculator. So if you go back to y equals, if you do want to make them different, hit the left arrow key till you get to the very end where you see like this little cursor thing is flashing. If you press enter on one of them, so I just move up and down to pick whichever one. So I press enter, it's going to make it bolded, right? So that's how I know that one's that. If I press enter more than once, it can do other things like, I wouldn't do that one because it actually fills it up. Although technically you could use this for inequalities, but like I said, with the way shading works on the older calculator, it'd be kind of hard to read it all. That shades it below. This makes like a little, I think we used to call it like a ladybug. Um, dots, and then this makes it dashed. So I don't think you have that many options on like the older calculators. Let's see, I think that's it. So now if we graph it, you'll be able to distinguish lines a little bit more. So like now that one's bolded, and that one, well, not really dashed, honestly, because of the pixelation. So that one doesn't work too great on this calculator. But that's kind of the basic ideas. You can change it up, but newer calculators, they have color, so you can definitely just rely on that. And from there, we'll learn how to do these intersect method to be able to calculate like, oh, where they're crossing and calculate that value. So that'll be our next thing. So yep, we graphed and we labeled each equation. So that's like the big thing. Now, what we're going to do next is to basically figure out what the test, the feasible region is. So that's going to be step 3. And so we will create a new slide. So step 3 is check for feasible region. And like I said earlier, you can kind of cheat this half the time. So I'm going to pick a point in here because to me it's bounded. Usually it's going to be there. In fact, like I said, a bounded region is guaranteed to have an optimal solution. So we kind of want to be in there. So we'll pick a point. We know that this is going to be, so if you solve for the y-intercept, you can kind of figure out what that's going to be. So for this y-intercept, how do we know what that is? Just set whatever equation crosses that point at equal to 0 because it's an x-intercept. So equation number 1, we're going to set that equal to 0. And so it's y minus, sorry, not y minus x, 4 minus x. And so x is equal to 4. So that's how we know that this is going to be 4. And from there, that means I just got to pick a number that's like right above it. So the number I will pick right here will be 4, comma. And then this is where it's kind of tricky because if you pick a number too big, you'll go outside of the box. I'm pretty sure 4, comma 1 will be fine. And, you know, from there we can kind of see it because it's right above it, right? So from that, we do 4, comma 1 into all inequalities. So the first one is x plus y has to be greater than or equal to 4. Again, do you have to do this? Technically, yes, because you want to make sure that it's true, like that it is the feasible region. You could always run into that situation where you think you picked the right point and then it's not actually true. So it's a good idea to do so, but sometimes, like I said, you can kind of skip it and you'll most likely be fine. But I have ran into a situation where I didn't do some kind of check like this, and it turns out that my work was actually incorrect. So 4 plus 1 is less than or equal to 6. So 5 is less than or equal to 6. So that's check, check. The next equation says, okay, x minus y has to be less than or equal to 4. So 4 minus 1 is going to be less than or equal to 4. So 3 is less than or equal to 4. Check. And then my next one is x minus y is less than or equal to 4. So 4 minus 1 is, sorry, not less than or equal to 4, greater than or equal to negative 4. And so 3 is bigger than or equal to negative 4. So check. So that right there tells us that this region is the feasible region, which means each of the corners that make up that feasible region is going to be a potential solution. One of them has to be the optimal solution. So it's either going to be that one. Okay. Actually, let me label it the way I did it earlier. So it's either going to be this one, this one, this one, or this one. So it's one of these 4 points. Okay. Are there any other corner points? When you actually look at the problem, there is no other corner points. Now, if you're wondering, what about this point? Is that a corner point? No, it's not, because the X and Y axis aren't boundaries. So you got to remember this, and this is kind of tricky sometimes. The X and Y axis are not boundaries unless I specify like X is greater than or equal to 0 or Y is greater than or equal to 0. So you have to remember that. So in a scenario like this, where there are only 4 corner points, you kind of limit your answer to only 4 options. Now, the reason I mentioned this is, like, I guess in a potential scenario where maybe this was the optimal region, then there would only be 2 corner points that you have to check, right? But again, you're not guaranteed that those would be optimal because it's an unbounded region. So whereas if you know your region is going to be the bounded one, then one of them has to be an optimal solution. So that's kind of the nice thing. Now, if you're wondering, before we do the corner point analysis, could I do this without having to, could I find the feasible region without having to plug in all those points? You could. So using the inequalities, right? First equation, I am bigger than 4 minus x, which means for equation 1, you would be all above. And then for equation 2, you are less than, right? Which means for equation number 2, I would have to be below. So we shade in below the second equation. So it's somewhere right here, right? It's going down. And then for the next equation, you are bigger. So for equation number 3, you would be bigger. So where's equation 3? You're bigger, right? And then for equation number 4, you are less than. So equation 4, where are you? Less than. So all of them are overlapping in the middle region, which means, hey, that's the feasible region. That's the one place where every single color is overlapping. And that means that's the feasible region, right? So whichever one overlaps all of them together. All right, so we check for that. Now comes the most important step, and that's going to be table. So when you're setting up all of this, this is where you're going to put all of your information, and this is where your final answer is going to go. So you're going to make a nice table. Okay. Plenty of space. And so we're going to have our points. So A, B, C, and D. And so the first part I put lines through point. So basically, you're going to write down which equations are making up that point. So for point A, if I go back to the graph, right? Point A is made up of equation number 3 and equation number 1, right? Equation 3, equation 1. So that's what makes up point A. So I'm going to write down 1 and 3, right? You could actually write out the equations if you want to, but I'm saying 1 and 3. And then I go to point B, which ones are making up point B? Equation 3 and equation number 2. So 3 and 2. And I will go back and I will say 2 and 3. And then for C, I go to the graph, equation 4 and equation 2. So 4 and 2. Or 2 and 4. Doesn't matter what order you write it in. And then for D, it's going to be equation 1 and equation 4. So 1 and 4. And we write that down. 1 and 4. There you go. And so from there, what you want to find is what is the actual XY coordinate of intersection. Now, sometimes it will be pretty obvious what it is. For example, The ones on the y-axis, those are the y-intercepts, right? So you can kind of get those ones for free. You could always put down the y-intercept ones, but the ones that are like the intersection of two lines that are not on the x-axis or y-axis, those ones require a little bit more work, so we're going to have to figure out what those are. And then from there, the last thing that you're going to have is your value. So basically, what is the maximum value? So the objective value. So when you get your coordinate and you plug it into your equation that you're maximizing or minimizing, what value do you get? And whichever one's the biggest or will be the maximum, and whichever is the smallest will be the minimum, right? And so now what we need to do is find the points of intersection, right? So that's what we're going to do next. And so what I'm going to do is take this and just copy it into the slide here so that we could have it as a point of reference and be able to calculate some values. So let's make that a smidge smaller. And so actually, okay, so then step 5 is going to be find points of intersection. And this part can kind of be annoying. So let's start with point A. And so generally, if it's a y-intercept, I always do those first, but I just go through A, B, C, D. So this is an x-intercept, but don't even think about it that way, because sometimes if you try to overcomplicate it, you might confuse yourself, or maybe you say x-intercept, but you put the y-intercept. So let's just set equations 1 and 3 equal to each other. So equation number 1, and if you're wondering, I don't remember what the equations are, well, let's just copy them down so that way we don't have to think about it. So I'm just going to copy these over here and put them right down here for us to remember. So 1, 2, 3, and 4. So for equations 1 and 3, we're going to set them equal to each other. And here's the best part. They're all equal to y, so I don't have to do any more manipulations. I don't have to worry about the inequality because it only matters when they're equal to each other. So equation 1 is going to be equal to equation 3. So that means I'm going to set 4 minus x equal to negative 4 plus x, right? And then you're just going to solve for x, right? And I'll write that down here, solve for x. So I add 4 over, and I get 8 minus x equals x. I add x over, 8 equals 2x. Divide both sides by 2. And then I get x is equal to 4, right? And we get that value. Now, if you're wondering, what is the y value, right? Well, if you do recognize that this is the x-intercept, then you know y is 0. But if you do not recognize that, then you're just going to plug it into whichever of the equations 1 and 3. So I'll plug it into equation number 1. Y equals 4 minus x. And so y is equal to 4 minus 4, and so y is equal to 0. And so I'm presenting it to you in a way where you don't have to think about intercepts or anything geometric. It's just algebra. I set one equation equal to the other. I solve for my first variable, and then I take that variable and I plug it into the equation to solve for the other variable. There is no geometry there that you have to think about, right? So that's kind of nice, right? It's just, it works for anything. So now we write this as an ordered pair, 4, 0. And we're good to go. I wouldn't do the objective value until you're done with all of your points. So then we go to the next one, B. So we're going to set equations 2 and 3 equal to each other. So for 2 and 3, we get 6 minus x is equal to negative 4 plus x, right? And so we just move some numbers around. It doesn't matter how you do it, just pick whichever way you like. So we get 10 minus x equals x, add the x over, and we get 10 equals 2x. And so if you divide by 2, and you get x is equal to 5. And then you're going to plug it into whichever equation you like. So I will do y equals 6 minus x. Again, this is equation number 2. This was equation number 1. And then I get y equals 6 minus 5. Y equals 1. So we get 5 comma 1. And we have another point, right? A question you might start to ask as you see the answers. I notice that a lot of my answers are kind of like symmetric, right? Like you start seeing that they start looking very similar. Is that a common thing? It can be. There sometimes is symmetry to these, but not always, right? So let's do this. Duplicate this slide. And then I'm just going to erase all of this and then keep going to C, D. And so this can be tedious at times. Like I said, when you get comfortable with the geometry, you can save yourself a lot of algebra because you don't have to actually calculate it. You just see where they intersect each other. And so often the geometry is faster, but it does require you to be able to interpret a little bit of it. So 2 equals 4. So we set equation 2 equal to equation 4. And so then we're going to subtract over the 4. Subtract over the 4. 2 minus x is equal to x. We add the x over. And then so 2 equals 2x. Divide over the 2. And then from there we get x is equal to 1. Right? And just like the last 2 examples, I'm going to plug it into whichever equation I like. Let's do equation 4, because that equation just looks nicer to me. Again, it doesn't matter which one you pick, as long as it's 2 or 4. And then I plug in 1, and I get y equals 5. And then you notice, hey, this is just backwards of the other one. Is that always going to happen? No, but it happens more often than you would think so. When in doubt, or if you're running out of time on an exam and you have like, 4 comma 0 and 5 comma 1, you could just write down 1 comma 5 and 0 comma 4 and hope for the best. And that would be the best guess because, believe it or not, you're more likely to get that correct than incorrect if you were to guess anything else, right? So just a little tip for taking the exam and if you had to guess something. So 1 equals 4. So we set those 2 equations equal to each other. 4 minus x. And then we set, what is it, 4 plus x. And then we just do the same thing we've been doing. So minus 4 minus 4. So negative x equals x. I add the x over. I get 0 equals 2x. Divide by 2, divide by 2. X is equal to 0. Right? So that's good. And then I pick equation number 1. And equation number 1 says y equals 4 minus x. Y equals 4 minus 0. Y is equal to 4. And so that gives us the last coordinate, 0 comma 4. Are these problems tedious at times? Absolutely. But like I said, you can also do this on your calculator, and I will show you how to do that. So my advice to you is if you wrote all 4, that's fine, but I would never analyze them more than 2 at a time. So for example, in the first one, 1 and 3, you can actually turn off graphs by doing this. So let me show you. So if you want to turn a graph off, hover your cursor over the equal sign and press enter. And notice that the equal sign no longer has a black box around it. That tells you that it's not going to show up when you graph. So let's just do 1 and 3. So I'm going to disable 2 and 4. So notice that 2 and 4 are no longer activated, so that when I press the graph button, it's only going to show these 2. Okay. Now, if you feel comfortable using a calculator, you don't have to disable them. But when you use the intersection feature, you would have to make sure you're on the right graph. So whenever you have only 2 graphs, if you do second trace, you have a couple of options. So all of these are extremely valuable. But the 2 that are most important, at least for us usually, are going to be 0 and intersect. Min and max are really good sometimes, depending on what kind of problem you're doing. But for us, we're either going to want to do intersect or 0. Now, for these problems, just use intersect. So we go to intersect. you press enter, and because these are linear lines, you can kind of cheat it, and you can just press enter 3 times. Enter, 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 and it'll give you the answer. If you have non-linear problems, then you would have to move the cursor so that it's close enough to whichever intersection point you actually want to calculate. But remember, linear lines only have one point of intersection, so it doesn't matter where the cursor is, right? So we got 4, 0, which is what we have here. And then I go back. Okay, now I want to do 2 and 3. So I'm going to turn off 1, and I'm going to go to 2. So one more time, you do second trace, hit the arrow key down to intersect, enter. Oops, I had to graph it first. Okay, and then now it says first curve. So you see the little cursor that is blinking. I'll move it over a little bit just so you can see it. So you can move it closer to the point of intersection, but for linear lines, you don't have to. But for non-linear, you will. So then you press enter. So first curve, second curve, press enter. Now it wants you to, it's confirming that you want to guess them. Yep, press enter, and then 5, 1, which is what we got. And then we do second y equals, oops, sorry, just y equals. Also, this is a side note. If you ever have issues graphing, like you're getting a dimension error or something weird, usually it's because you'll have is a stat plot turned on. So I'm going to try to replicate it. I don't think it will happen. But if I hit graph, you see how it says invalid dimension? If you ever get that error, the first thing I'd recommend you do is do second y equals. Let me quit. And make sure that these all say turned off. If they don't, click whichever one says on, press enter, and then hit the right arrow key and turn it off. That will often fix a lot of your problems with graphing if you ever have that issue. So then we do second trace, intersect. Actually, did I turn it off? 2 and 4. That's what I wanted to do. Nope. So 2, turn 3 off, turn 4 on. Now we do second calc, intersect, press enter, takes a second to graph it, and then you press enter again, guess, 1, 5. We have that right there. And then just for the sake of completion, let's do 1 and 4. So turn on 1, turn off 2, second calc, intersect. There it is. Second trace, intersect, enter, guess. There it is. 0 and 4, which is all of the ones that we got. Now, you can always use this, but make sure that you read the directions, and if they say you must show your algebra, then show your algebra and use this to check your answers. But if you don't show algebra, sometimes you can get no points, or they'll take off points for not showing work. So make sure that you pay attention to that. All right, so then our final step is going to be step 6. Calculate values for objective function and find max or min. So in these problems, it's always almost going to be one is you're either looking for a max or a min. So let's just copy over the table right here. Don't need that anymore. And so we found that this was 4, 0, 5, 1, 1, 5, and then 0, 4, right? And so now I just plug it in. So this is the x value, that's the y value, x and y, x and y, x and y. So p is equal to 4 plus 2 times 0. P is equal to 5 plus 2 times 1. P is equal to 1 plus 2 times 5. And then P is equal to 0 plus 2 times 4. And if you calculate it, which one is the biggest? I get 4. I get 11. Nope, I do not get 11. That's bad math. I get 7. This one is 11 because 10 plus 1. And then this one is 8. So this is the largest. So that means that this is the maximum. And there is our answer. So the value of x equals 1 and y equals 5 are the maximum. Or x comma, sorry, 1 comma 5 is the max. And in the context of a word problem, you'd be like, I would need 1 chicken and 5 rabbits to maximize my farm for some kind of problem. So now let's do an example of minimization. It's the same problem, just now we're minimizing. So we're going to minimize c equals 8x minus 8y subjected to all of these conditions. Now, what's interesting about this problem is the x and y axis are now going to be boundaries, which means you have a lot more closed regions. So again, just because you have a closed region doesn't mean that that's the one that has the solution. You still have to find which one is the feasible region. So that's what this example is going to illustrate. But the nice thing is every problem's the same. But the bad part is they're all the same. So that means you have to do all these calculations. So step 1 is to isolate y. So for the first equation, me personally, I always like to have y on the left side because that's how I read y equals equations. It's not a necessary thing you have to do, but it doesn't hurt to do that. So if you ever want to flip an inequality, so you can flip inequalities, the rule is though, if you do that, you have to flip the inequality with it. You don't have to do that for an equal sign because an equal sign doesn't flip because it's equal. So that's my first equation, equation number 1. Then I go to the next one. I don't have to make any modifications. So y less than or equal to 2/5 x. Well, no modifications necessary. So no change. Just going to write that there in case someone's like, what did I do? I did nothing. For the next one, we are going to solve for y. So we're going to move the x over, and we get y is greater than or equal to 7 minus x. So that's equation number 3, like that. And then for the next one, we are going to do the same thing. So x plus 2y is less than or equal to 16. And then for this one, you're going to move over the x, and then you're going to divide out the 2. So we're going to move that over. And so we get y is less than or equal to 8. Actually, I won't draw that. Minus 1/2 x. You could use decimals, and in fact, in some problems, I would recommend decimals, but I would never recommend decimals for like a third or like, point, like repeated decimals, because if you do that, then you have to basically cut it off at some point, and then you introduce rounding error. So just be careful with that. And then the last ones are just going to be x is greater than or equal to 0. It's equation number 5. And then y is greater than or equal to 0. One thing to note, x greater than or equal to 0, you actually can't draw that on your calculator. You can't draw vertical lines. So that's one that you'd have to do visually. So just keep that in mind when you're doing that. So that is all of our equations. And if you, again, for anyone that's watching this or just kind of skipping through, we just divided the 2 over. So we did this, divided the 2 over, and then that's how we got the y is less than or equal to 8 minus 1/2 x. So in case anyone was curious, we just divided the 2 over. Okay, so we have all of our equations. Now let's graph. So step 2 is to graph and label. So here's a nice thing too, and you should always use this. If you have these equations right here, just mean quadrant 1. So you don't have to draw the negatives, right? No negatives. So you can make a nice graph like this. Now, I do recommend you draw the arrows going past it, so that way you know which one is which. But the cool thing is you don't have to really think about the negative region. So equation number one, x fifths, sorry, 1/5 x, there is no y-intercept in that it's 0. So the first equation, so 1/5 means it's going to be kind of flat. So let's do that. So that's equation number one. Equation number two is 2/5. So it has a slope that is slightly bigger. So I'm going to exaggerate it a little bit, but it's going to look like that. All right, so that's equation number two. That's a little bit better. Equation number three, that has a y-intercept of 7. So let's put a 7 up here. And then I do have a y-intercept of 8. So let me make that one 8 and make that one 7. And then no other y-intercept, so that's a good thing. So 7 and then negative x just means I go down like that. And then for 8, I have negative 1/2 x. So you got to be careful here. So the more negative you are, the steeper you are going downwards, right? And then the less negative or the closer you are to 0, the flatter you're getting. So the 8, right? The 8 minus 1/2 x, that's actually going to be a little bit flatter and it's going to look like that, right? So you got to be careful with the negative ones because they often are very tricky. Okay. And so those are my lines. And so now I have to figure out what is the feasible region, right? And like I said, in this class, you can kind of cheat it. It's going to be this one, most likely. Like that's what I would guess first. If it's not that one, then my next guess would probably be this one. And if that's not true, then I would guess this one. Okay. And if that one's not true, then I'd probably guess this one. And if that one doesn't work, probably this one, then this one. And then the last ones I would check would be this one, and this one. Because those are unbounded regions, right? Again, you have to check to make sure you're picking the right corner points, because if you did this region, you would have to check the corner point here, 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 and here. Like you'd have to check those 4 corner points. If the region is somewhere like right here, then you only have to check this corner point and that corner point, right? So knowing which is your feasible region tells you which corner points that you're going to have to actually analyze. And like I said earlier, you could always kind of cheat this with the inequalities and kind of shading, right? So for the first equation, you have to be bigger. So that means shade upward. So equation 1, I'm going to shade up, right? And then equation 2 says less than, so I'm going to shade down. Also, you can only use this idea if all of your y's are on the left side, like they're all in the same direction. If you have y's going in different directions, you can still do it. Like it's not incorrect. It's just like not easy to see it for most students. So equation 2, we're going to be less than, which means we're going this way, right? So we're shading down. And then equation 3 says, okay, now we're going to be greater than, so above equation 3, so we're shading upwards. And then equation number 4 says we are going to shade downwards because we're less than, right? So equation 4 is down here. And we notice that they all overlap right here. They all overlap in that little box. So that there tells me that's the feasible region. So do you have to show the work of checking? If they don't require you to on the exam, then yeah, you don't have to show any of the work. And you could just use this idea and not have to worry about it. Okay, but I'm going to do it for you. I'm going to show you the work just so that, you know, you have a reference point for it. Let me give myself enough space here. Move that over. So step 3 is check feasible region. So I personally think it's going to be somewhere in here. Now, this is tricky just because I have to find a coordinate that's in there, right? It's very easy to pick a coordinate that's not in there. So how would I personally do that? Again, you kind of have to do a lot of extra work. So I'd have to find maybe this coordinate right here. And if I found that coordinate, I would just go slightly below it. So that's where the line number 2 intersects with line number 4. So I would personally use my calculator for this. Again, in this kind of problem, this is probably like annoying to do. So that's why I tell students 9 times out of 10, it's going to be the region like this, right? It just usually is. So you can, if you wanted to take the risk, just go for it. But if you want to be like super technical and be absolutely sure, what I would do is just graph lines. Let's see, line 2 and line 4. So we're going to have to eventually plot all these anyway. So let's just do it now. So let's clear that, clear that, clear that, clear that. And so we're going to do x divided by 5, 2x divided by 5, 7 minus x, and 8 minus 1 divided by 2x. And like I said, I only want equations 2 and 4. So let's hide this one. Let's hide this one. And then I'm going to graph them. And then I will do second trace. And then where do they intersect each other? Enter, enter, enter. 8.888 and then 3.555. So unfortunately they're fractions, but I can kind of use that as a baseline. So it's going to be somewhere right here. So if I want to go slightly below, I would do 3. And for my x value, I will do like 8.7, right? Because that should be good enough. So if I go down 3, actually, no, I can still use that y value. I'm just going to move the y value down a little bit. So I'm going to do 8.88 comma 3. And that should be like right here. Again, this is just to make sure that this is the correct region. Technically speaking, you could just skip this step and risk it. And like I said, 9 times out of 10, this will probably be the region that is the answer. So let's just check using the original inequalities. So 8.888 over 5 is less than or equal to 3. So that's equation number 1. And so 8.555, let's just double check, second quit. 8.88 divided by 5 is equal to 1.76. Check. And then I do 3 is less than or equal to 2/5 times 8.88. And so what I end up getting here, let me just move this over a little bit. So 3 is less than or equal to, so 2/5 or 0.4, that's 2/5 times 8.88 is 3.552. So check. 3 plus 8.88, except I did that backwards. Let me make sure I do that correctly. 8.88 plus 3. Not that it's incorrect mathematically, it's just wouldn't make sense for the variables. And so I get 11.88 is greater than 7, so check. And then the final 3, 8.88 plus 2 times 3 is less than 16. So hopefully this one doesn't break. So 8.88 plus 3 times 2, or 2 times 3 really, 14.88 is less than or equal to 16, so check. And then 8.88 is greater than or equal to 0, and then 3 is greater than or equal to 0. So it satisfies every single constraint, which means, okay, so that single point that I picked right here, 8.88 comma 3, the entire region that it's inside, so the bounded region, use lavender, is the region of our optimal solution, which also means the corners that make up this region are going to be an optimal solution. One of them has to be, right? So A, B, C, and D. And again, if you're wondering, why do I have to do this? Like, what value do I gain out of doing this analysis? Well, think about it. There are, and I didn't draw them earlier, I should have, So the fifth equation, x is greater than or equal to 0, is the y-axis. So that's equation number 5. And equation number 6 is the x-axis. That's equation number 6. Let's count how many total corner points that you could actually analyze. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 total corner points that you could analyze, right? Do we want to analyze all 9 of them? Not really. So by finding the feasible region, I eliminated 9 total options for corner points, and I have brought it down to only 4. And 4 is less than 9, which is better, right? Imagine a optimization problem that had like 100 points, and then the optimal region was only 5, right? 5 points is way less than 100. So that's why we do it. Okay. So, but again, if you want to be like a risk taker, you could just skip this step, hope that this is the general region. Like I said, usually it is, not always, but, and we'll do an example where it's not. But usually it's going to be something that looks like this. It's usually like the one in the middle that makes up like a, 4-sided shape, and you'll be good to go. So now we do step 4, which is make the table. So step 4 is table. So we're going to make a nice table here. And this will be our point. So A, B, C, and D. There is no like absolute rule like how you should label your corner points. People like to go clockwise, or most people like to go counterclockwise, but you could go clockwise. You could start at the top. But again, from what I've seen in the textbook and just general notion, a lot of people like to start at the bottom, like the most bottom point, and go counterclockwise. Like that's kind of usually what I've seen. But it doesn't matter. And usually on an exam, you can label it however you want. Or if they're kind of being nice, they'll label it for you and just tell you. Okay. And so this is going to be lines of intersection. Right? So which lines are intersecting each other? And so if we look, and you know what? Let's do it this way. Let's just bring this graph over here so we can kind of look at it together. And then I'll make a new slide for the algebra. Paste it as a picture. Actually, no, I don't want to do that. Actually, yes. There we go. So we just want to know what line's intersecting. So at A, we have 1 and 3. So 1 and 3. Right? And then for B, we have equation 1 and equation 4. Right? And so, like I said, being organized here is important because when you have so many lines, things start to kind of blend in with each other and you have to really pay attention. For C, this is equation 2. And I'm just going to actually also write it up here because the way that I drew it down here kind of looks a little confusing. So just to make it more obvious. And actually, I'll do that over here too. So this is 2 and this is 1. We have for C, equation 2 and equation 4. So 2 and 4. And then for equation D, we have line 2 and equation 3. So 2 and 3. And some people will write the equations in the table. I usually don't, just because sometimes it gets really cluttered. So as long as I have the equations somewhere nicely, like right here, it's usually, you don't need to do that. And then after that, you're going to want to include your XY coordinate of intersection. Once you make the table once, you don't need to make it again, right? Actually. So x comma y of intersection. And then here is going to be your objective value. And so what we end up getting is C equal to 8x minus 8y, like that. And so now we have our table set up. And so from that, we can start calculating all of the points of intersection and then start calculating the maximum value. So that'll be our next step. And so we'll paste this right here just to have it as a frame of reference. And now let's start doing all of the algebra. Now, the nice thing is you're only ever going to do this for linear lines, at least in this class. So linear lines, the algebra at worst is just you have to divide some numbers over, subtract. This would become a lot more annoying with non-linear problems because then you have to do like maybe quadratic formula and stuff like that. So step 5 is going to be find corner points. So that's really what you're doing. You're finding the corner points. So find corner points. So for corner point A, we're going to do 1 equals 3. So let's just copy down all of these equations for ourselves. And then we can just start plugging away. And again, geometry can save you a couple of points if you pay attention to where, like if it's a y-intercept or x-intercept, then you don't have to do any algebra. You can just put it down immediately. Unfortunately, with this problem, none of them are y or x-intercepts. They're all intersection points, so we have to calculate every single one of them. So for the first equation, it's going to be x over 5 equal to 7 minus x. So this will have fractions, which, never too fun, but I will show you how to use your calculator for these so that you don't have to do like, fraction calculus or fraction arithmetic. X over 5, so the opposite of division of 5 is the multiplication of 5, so I multiply both sides by 5. And so x is equal to 7 minus x times 5. I'm going to distribute the 5 into each term. X is equal to 35 minus 5x. And then from here, I am going to add the 5x over. And I get 6x equals 35. And then I divide the 6 over, and I get x equals 35 over 6. And there it is. Is that the optimal way of doing it? Everyone can do it differently, right? I could have just added over the x and done it that way, but it's a personal preference. You do it however you like in terms of the algebra, right? So we're going to plug this into equation number. Actually, no, equation number 1's fine. No, actually, I prefer equation. Yeah, no, equation number 1's fine. So y equals x over 5. So this is important because sometimes students forget how fractions kind of look. So remember, x over 5 is equivalent, right? It's the same thing as y equals 1/5 times x. So x over 5 and 1/5 times x, those mean the same thing. So they're not different. And the reason I do this is because it makes this a lot easier. So 1/5 times 35 over 6, like that. And the multiplication of fractions is just you multiply straight across. And so you get 35 over 30, like that. And there it is. So my ordered pair is going to be 35 over 6, comma 35 over 30. Not the most elegant answer, but that is the correct answer. Now, on the homework, if they really, really want you to simplify the fraction, or the exam for that sake, if you ever want to simplify fractions, you would just do 35 divided by 30, hit the math button, press enter on frac, and that'll simplify the fraction for you. So that's 7 over 6. So you could simplify if they make you. It's not always required. Or you can write it as a decimal. I'd only write it as a decimal if it's a really nice decimal, or if the homework requires me or the exam requires me to convert to a decimal. So that's the first coordinate. The second coordinate is going to be 1 and 4. 1 equals equation 4. Sorry, equation 1 equals equation 4. So that's going to be x over 5. And that's going to be equal to 8 minus 1/2 x, right? So again, you can do this however you want. You could add over the 1/2 x. So I'll show you how to do that way. I prefer to multiply the 5 over and do all of that, but let's just add over 1/2 x plus 1/2 x, right? And so 1/2 plus a fifth, right? Again, can you find common denominators and all of that work? Absolutely. Or I could say 1 divided by 2 plus 1 divided by 5, hit the math button, hit frac, and then I get 7 over 10. My calculator did the work for me, like that. And you could convert it to a decimal if you want to do it that way, right? So you could do, okay, 7/10, right? If I press enter on 7 divided by 10 into a decimal, that's just 0.7. So 0.7x is equal to 8. I divide over the 0.7, divide over the 0.7, and so x is equal to, so 8 divided by 0.7, 11.42857. I don't like that answer. It's, an ugly decimal. So I'm going to hit the math button, hit frac, and then I'm going to convert that to a fraction, 80 over 7. Right? Again, how you want to do this is completely up to you. Maybe you prefer to do it a different way, and that's perfectly fine. But just make sure that you always answer the question in the form that the either exam or the homework wants it, i.e. either fractions, decimals, simplified, or not. So equation number 1 is 1/5 times x. So then y equals 1/5 times 80 over 7, which is then 80. And then, so 1 times 80 is 80, 5 times 7 is 35. And you can simplify that because they're both divisible by 5. 80 divided by 35, math, frac, 16 over 7. And so my ordered pair, make sure to emphasize that that's a y equals, is going to be 80 over 7, comma 16 over 7, right? Now, if you're wondering, why am I writing it as a fraction and not a decimal? Like, is there a purpose for that? Again, it just depends on the homework or the exam. But sometimes if the numbers are super close to each other, writing it as a fraction just makes it more exact. Sometimes the decimals, if you round, can make the answer slightly off. And if the optimal solutions are so close to each other, you could always run that risk of missing it. So that's why. But whether you do fractions or decimals doesn't actually matter. So let's do the last two coordinates. Actually, what am I doing? I could just duplicate this. And so now we're going to do C and D. So for C and D, it's going to be 2 and 4. So setting 2 and 4 equal to each other. So 2/5 x equals 8 minus 1/2 x, like that. I just want to make sure, because, yep, that was, so it's the same problem. You're just going to subtract over or multiply over. So if I add 1/2 x over, I'm going to make sure I added it over last time I did. Okay. So I'm going to add 1/2 x, and so 1/2 plus 2/5, I think is going to be 0.9, but doesn't hurt to practice doing this. So 2 divided by 5, math, frac, yep, 9/10 equals 8. And again, if you want to do it without doing the fractions, or sorry, the decimal, so this is the way you would do it, just fractions, you can multiply both sides by the reciprocal, because that would cancel it out. So 10 over 9, And then what you do to one side, you got to do to the other. Cancel, 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 cancel. X is 80 over 9. And remember, when you multiply a number by a fraction, every single number has an invisible number 1 underneath it. So you could convert any number into a fraction and keep going. So in case you forgot that. So that's probably the fastest way of doing it overall is so adding the fraction over and then just multiplying by the reciprocal. Again, whichever one of these variations that I have shown you makes the most sense, just use that one for every single one. So that way you don't confuse yourself. And then I'm going to do equation number 2, again, just because it's the nicest looking one, like that. And so from that, we get y equals 2/5 times 80 over 9, right? If you don't want to plug this into your calculator, you could use something like cross cancellation. So the 5 goes into the 8, would that be 16 times? And then so that's 5, and that becomes a 16. So then you get 32 over 9. So again, there's so many little arithmetic tricks that you can use, but kind of a personal preference at that point. And just to verify that that answer is correct before I move on, 32 over 9. Yep, we're good to go. And we have our next value. If you're wondering, is it always going to be that like the denominators are the same? Pretty much. Once you use one denominator to solve a value, it typically remains with that denominator. The exception would be is like if you get something super nice like a half or something like that, sometimes it could simplify even further than your common denominator. But if your common denominator is an even number, they typically are, that's the one where they usually like simplify further. If they're odd, typically they stay the same, but there's no absolute rule on that. All right, last one. I know this is taking forever. 2 and 3. So equation 2 and 3, 2/5 x equals 7 minus x. So I'm going to add x over, and I am going to get 7/5 x equals 7, right? 2/5 plus 5 over 5 is 7 over 5. And then I multiply both sides by 5/7. 5/7. Cancel, 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 and x is equal to 5. So for once, we get a nice number. And then for this one, I'm going to use equation number 3, just because that one for this one specifically looks a lot nicer. And so 7 minus x minus 5. And so y is equal to 2. So we have the coordinate 5, 2. Just like that. So now we have all of our corner points, right? And so the last step that we have to do from here is just to plug in those points into the table and we get our answer. So that'll be our final step. So step number, in this case, it would be step 6. Plug in corner points into objective function. So we get C is equal to 8 times 35 over 6 plus, sorry, not plus, minus 8 times 7 over 6. C is equal to 8 times 80 over 7 minus 8 times 16 over 7. C is equal to 8 times 80 over 9 minus 8 times 32 over 9. And then C is equal to 8 times 5 minus 2 times 8. And one thing about this is the closer the numbers are together, the smaller it's going to be. And then the further apart these numbers are, the bigger they're going to be, right? And so if you plug these into your calculator, you'll get something like 37.3. And one decimal place for a lot of these is fine. 73.1. And then 42.67. Sorry, that'd be 7. And then the last one is 24, right? And so we always have to remember, are we maximizing or are we minimizing? So just go back to the directions to verify. And so if we read at the very beginning, we are minimizing, right? So that means what is the smallest value? And so 24 is the minimum. And so the minimum values are x comma y equal to 5 comma 2. And there's your answer. Now, a lot of the times we are interested in knowing what the values are that minimize it. But other times we also want to know what is that value. So for C equals 24. So always pay attention to the problem. Do I want the values that minimize it, or do I want to know what the minimum value is? So often, like I said, the X, Y value is actually what matters, not the C value. But in some cases, they're both valuable. So now let's do an application of this with a word problem. So you make dog food out of chicken and grain. Chicken has 10 grams of protein and 5 grams of fat. Grain has 2 grams of each, so 2 protein and 2 fat. A bag of dog food must contain at least 206 grams of protein and 176 grams of fat. If chicken costs 9 cents per ounce and grain is 1 cent per ounce, minimize the cost, right? So this is an interesting problem in that you have to think about it in the sense of what mix of ingredients will yield the cheapest result, because chicken will cost more than grain. But sometimes you can actually cheat these problems if the cost difference is so dramatic that you can kind of tell what the answer is gonna be. So this is a good example of that, right? If chicken costs 9 cents per ounce and grain is 1 cent per ounce, so like almost a 10 times difference, but the difference in nutrients is 5 times, and I guess 2.5 times. The cost is so much cheaper compared to like how much extra protein and fat you gain from chicken, that the answer is most likely going to be a formulation of all grain, right? So that is actually going to be the optimal solution here. An entire grain-based food. Now, who would want that for a pet would depend on the person. We would prefer a mix, or some people prefer all chicken, no grain. But that's just something to think about, is like when the cost is that much cheaper, that's why companies do it, even though maybe it's not as healthy for certain dogs and stuff like that. So step number 1 is to reread problem. Right? Always reread it. That's always important. And then once you've done that, we're going to label our variables. So label variables. So the thing that we're trying to optimize here, okay, is cost, right? We want this to be as cheap as possible. So what is constructing the cost, right? Like what makes up the cost? It's how many ounces of each that you use, right? Not the protein and not the fat content, but rather how much of each you're using, right? So we're going to say X is equal to chicken ounces, and then Y is equal to grain ounces. And this is an interesting problem, and this is just an interesting in like the context of like nutrients. We're weighing food in US customary ounces, but the way we measure nutrition is in metric, right? So thankfully they're not interacting with each other, so no conflicts of units. So now that we have our variables, the first thing you need to figure out is what is your objective and what are your constraints. So objective equation. So what are you trying to do? I'll do these separately. So the thing I am trying to do is I'm trying to minimize the cost. Like that's my goal. It's either a min or a max problem, right? Here we're minimizing. So my cost is going to be minimized, right? That's what I'm trying to do. So C is going to be equal to however much chicken you use and however much grain you use. But you have to spend money on each ounce, right? So chicken cost 9 cents, right? I didn't realize that. That should be chicken. Costs 9 cents per ounce, and grain is 1 cent per ounce, right? So we're going to do 9 cents, which we have to convert to dollars, right? So if you wrote the number 9, you'd basically be saying $9 essentially, if assuming everything else is equal. But you could technically use 9 as long as you know that your final answer is in cents, not dollars. So 9 cents per chicken ounce, and then 1 cent per for grain ounce, like that. So that's our equation. That's our objective. We're going to use it to calculate the values at the end. All right, step 4. All right, what are your constraints? Not every constraint is going to be listed explicitly. Sometimes you will have to think about natural constraints. What are some things that I don't have to say, but you have to realize is true? Okay. So the first thing that they say is I have to have a minimum, so at least 206 grams of protein, right? So that means for every ounce of chicken, so I get 10 grams of protein for every ounce of chicken, plus 2 grams of protein for every ounce of grain. That has to be bigger than 206 grams of protein. So that's the protein one. And then for fat, we have 5 grams of fat. And then we have 2 grams of fat. And that has to be at least 176, right? So that's going to be your fat equation. But there are 2 other equations that you have to consider. They are not given, but if you think about it logically, it would make sense. If you don't use any chicken, then how much protein would you have, right? Or if you didn't have any grain, how much fat or protein would you have? So the question then becomes, can I have negative ounces of chicken or can I have negative ounces of grain? And the answer is no, because that doesn't make sense logically. So these both have to be greater than 0, right? And we call these natural boundaries, right? Natural in the sense of they make sense in the context of, natural, like nature. Or another word that's much more used is a practical boundary. They're practical because it doesn't make sense to talk about negatives in this context, right? Can you have a negative cost? Yes, you could technically. But can you have a negative amount of mass? No. So, or I guess in this case, weight. So then step 5, after we've done that, is to graph. So now we're going to graph. And so we'll just do graphing, okay? So we graph. And so, oops, skipping a step here. Isolate y. We should isolate y first. So let's isolate y in all of these equations. So 10x plus 2y greater than or equal to 206. So I'm going to subtract the 10x over. Divide the 2 over. And so y is greater than or equal to 103 minus 5x. And so then the fat equation will be 5x plus 2y is greater than or equal to 176. And then I subtract the 5x over. Divide the 2 over. Y is greater than or equal to, in this case, it would be 88. Minus, and I'm going to do 2.5x. I'm going to actually convert it to a decimal here, just because that number is easier to look at. So we have our equation number 1. And we have our equation number 2. And then we'll call this equation number 3 and equation number 4. Actually, I'll just write them over here. X is greater than or equal to 0. That's equation number 3. and then y is greater than or equal to 0. It's equation number 4. So now we can graph. So step 6 is to graph. Again, because of the x greater than or is equal to 0, y greater than or equal to 0, I don't have to worry about negatives. And then we graphed our equation. So equation number 1 has a y-intercept of 103. And then graph number 2 is going to have a y-intercept of 88. So that's what I would always draw those first, right? What are the y-intercepts? So equation 1 has a negative slope of 5, which means it's going to be steeper. Going down. Again, it's exaggerated. It's not exaggerated here. And then the 88 and the negative 2.5. So the negative 2.5 is closer to 0. So that's going to be a little flatter. So it's going to look like this, right? So that's equation number 2. That's equation number 1. And then equation number 3 is just the y-axis. And equation number 4 is just the x-axis. You don't actually have to draw this one, but it does help realize what it could be. And so just visualize, like, what are all the possible corner points? That's a corner point, 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 that's a corner point. So those are all of my possible corner points, right? And so in this problem, we need to figure out what region is the feasible region, right? And like I said, this is an example where if you don't check and you just kind of go with what you've been seeing, you can actually mess up, okay? Because, you know, usually if I had to guess first, I would guess this region. Like, this is the first region that I would guess, because that's what I instinctually think it would be. But we're going to see right now, that's actually not the one that we want, okay? It's actually going to be this one out here, right? And if you use the inequality analysis, just using the shading, the first equation says greater than, so it has to be bigger. And then the second equation says also has to be bigger. So that means, sorry, like that. They're both overlapping in the big region, so like right here, which means that's the correct one, right? But if you just kind of do it mindlessly and forget that you have to check, then it's very easy to overlook that little detail. So that's what we're going to do in the next step. And as you do this over time, you can cut out a lot of the steps or condense them down if you want, which I would recommend you do. So now let's check the feasible region. So step 7 is to check the feasible region. Like I said, my first instinct, not knowing what's going on, is to pick a point right here. And the easiest point here would be 1, 1. So 1, 1, right? I mean, technically you could do 0, 0, but I'm going to do 1, 1 just to be safe. And so I take my equations, or my my constraint equations, which I'll just copy over here since they were not given to me. So these are my constraints. And so I'm going to check, okay? 10 times 1 plus 2 times 1 has to be bigger than 206. So I get 10 plus 2 greater than or equal to 206. 12 greater than or equal to 206. Nope. So this is not a good region. That's actually bad. Now, personally, would I check all of the closed regions first before I check the open one? Yes, that's what I personally would do. I would then check this one and then check this one. But because, you know, in the context of this problem, I could probably check this one quickly because it's much easier for me to figure out what a point is in that region. Whereas in the two smaller ones, I kind of have to think about it first. So what I'm going to do is I'm actually going to pick a region point out here, just because I can easily pick something. So for this one, I can do, I don't know, like 400, 400, like 400, 400 somewhere out there, right? So I'm going to do 400, 400, just because that's really far into that region. So and you could do whatever you want, but I'm going to do 400, 400. And so what I end up getting is 10 times 400 plus 2 times 400 is greater than or equal to 206. And so I get 4,000 plus 800 greater than or 206. So 4,800 is greater than 206. Check. Then I go to the next one. 5 times 400 plus 2 times 400 greater than or equal to 176. 2,000 plus 800 is greater than or equal to 176. 2,800 greater than or equal to 176. Check. So my feasible region is going to be over here. Okay, it's going to be out here. So then my question becomes, okay, what are the corner points, right? Well, the corner points are going to be right here, that point of intersection, right here because they intersect each other at that moment, and right here. Okay, so those are my points of intersection. Now, because this is an open region, it does not matter, sorry, it is not guaranteed that one of those is an optimal solution. One of them can be, but there's no guarantee of that. So there could be a scenario where there is no minimum value, right? That is possible. A closed region will always guarantee one. So that's something to consider. So now we will look. And the next thing we're going to do is make our table. So let's label these. And I label these as A, B, and C. So A, B, C. And then step 8, which let's do that on a new slide, is we're going to make a table like that. And thankfully, we only have 3 points, so not 4 points. So A, B, and C. And then let's just copy the graph over. Just have it right next to us. So now we do our points of intersection. So lines of intersection. So for point A, B, I forgot they didn't copy over, so I'll just write that down real quick. So A, B, and C right there. The lines that intersect for A are going to be line number 2 and 4. So 2 and 4. Sometimes it is kind of hard to read. You just got to make sure you make it neat. And then for B, it's going to be 1 and 2. So equations 1 and 2. Right? Equation 3 is the y-axis. Equation 4 is the x-axis. And then C is going to be equation number 1 and equation number 3. Now, here's the nice thing about A and C. They are the x and y intercepts. So you actually don't have to go through the hassle of solving them, like, you know, in the context of all of the algebra that we use. But you can. And if you feel more comfortable just using that methodology, then by all means. The x comma y of intersection. And then the objective value. And so our equation is we're minimizing cost. So cost is equal to 9 cents per ounce of chicken plus 1 cent per ounce of grain. So that's what we're trying to optimize, right? So now let's find corner points. Find corner points. So we'll start with A, and we're going to set equations 2 equal to equations 4. And so I want to show you something here on the calculator. So the intersect feature is always very nice, right? You could always use the intersection feature. But you could also, if you know it's an x-intercept, right? If you know it's an x-intercept, you could also just use the, what's it called? The zero function. So I'll show you how to use that in a moment. So let's just organize these a little bit better. That should work. And then let's go to our calculator. Let's do y equals. Let's erase all of these. And then let's type them in. So for the first one, 103 minus 5x, 88 minus 2.5x. And then I would not write these two because you don't need to. So this is what I would recommend you do. So for the first one, it's going to be 2 and 4. So equations 2 and 4. So equation 2 is 88 minus 2.5x equal to y 0. So again, this really is the x-intercept. That's what you're solving for, the x-intercept. So what you could do instead is go to, so we're going to get rid of equation 1 because we don't want to analyze that right now. And we're going to do graph. So this is the graph. Now, notice that nothing showed up. It's because our window is small, and then the value is like 88 minus 2.5x. So the first thing I would do is I would do like a zoom. So I always do zoom 6, but that's not going to work here. So if that doesn't work, then I just press zoom out. So looks like it's getting stuck. That's not good. So if you ever get into that issue, you got to just turn it off and then turn it back on. Okay. So yeah, if you ever get stuck graphing something, like the little dots stay there, just turn it off and turn it back on. So I'm going to do zoom, and then I'm just going to zoom out. So let's zoom out. Right? Nothing is, so now I got something, right? And then I want to zoom out one more time. So let's just zoom out. And that's better, right? That's good enough for me. If you actually want to be more specific, go to window and then just change like your maximum Y value or minimum value so that it only shows like a much smaller window of the values that you want. Okay. So then I'm going to do second calc, and then I'm going to go to 0. Okay. Now the way it works is you need to pick a little dot on the left side of your 0, your x-intercept. So it's on the left side of the little 0. Press enter, and then move the cursor to the other side. Press enter one more time. 35.2 comma 0. So it tells me right there what the x-intercept is. Again, you don't have to do it that way. You could just also solve this directly. So if I add 2.5x over, I get 88 equals 2.5x, divide over the 2.5, and then x is equal to, and again, our calculator will tell us that. So 88 divided by 2.5, 35.2. I might have said 36, but it's 35.2. So you got the same thing. So there's the x value. And then to find the y value, you just plug it into, well, you got to plug it into the second equation. You don't have a choice because the other one's just y equals 0. So that. And what you end up getting. Now, if you think about it logically, you should know what you're getting because it's the x-intercept, but just to drive the point home, 35.2, run out of space, let me make that bigger. It's the x-intercept, right? So the y value should be this number every single time. But in case you're not like actively paying attention to that, if you plug it into your calculator, 88 minus 2.5 times 32.5, sorry, 35.2, you get 0. But think about it. What did you set equal to 0? You set y equal to 0, right? So y should be 0. And then equation number 4 also says that y is equal to 0. So our coordinate is 35.2 comma 0. So what case is this when you think about it in the terms of the context of the problem? This is the all chicken case. So what if I made a recipe with just chicken? Only chicken. Well, think about it. If you only use chicken and chicken is 9 cents per ounce, that's going to be the most expensive one, right? So we kind of already know that's not going to be the correct answer, but you can think about those kind of things as you're doing it, right? The most expensive ingredient, the optimal solution is going to be to only use that ingredient. Preferably, we want a mix of the two. But again, this is a problem where if you think about it, the other ingredient is so much cheaper, you could just basically use all of the cheapest ingredient and still be cheaper than any mix of the two. But we'll see that in a moment. Now I set equations 1 and 2 together. So 103 minus 5x is equal to 88 minus 2.5x. In this case, I'm going to add the 5x over. One looks nicer to me. So 103 equals 88 plus 2.5x. 5 plus negative 2.5 is a positive 2.5. Subtract the 88 over. I get, what would that be? Negative 15, or sorry, 15 equals 2.5x. Yep. And then divide over the 2.5, the 2.5. And so x is equal to, and I believe it's going to be 6, but let's just double check. 15 divided by 2.5. Yep, it's 6. And then if I plug that into either equation, so let's plug that into equation number 1. Y is equal to 103 minus 5x. I just chose that one because it's 5 instead of 2.5. It's a nicer number to me. So then I get 30. And then I get 73. So in this case, this is the 6 ounces of chicken and 73 ounces of grain, right? So that's that scenario. It's a mix of the two. And if you're wondering, what do these actually tell me? These coordinates are basically satisfying the condition that you have enough protein and enough fat to satisfy some kind of nutritional guideline, right? We want to make sure that the food that we're feeding to our pets meets a certain number of nutrients so that they're healthy, right? If a manufacturer was below this, then the food that they're selling is not nutritional enough to feed a pet for the long term, and that could lead to health issues, right? So that's kind of the idea behind this, okay? And then for C, what we're going to do is the same thing. We're just going to calculate it again. So for C, now C is actually the easiest one because if you look at the graph, it's the y-intercept. So you wouldn't even need to do anything. You could just be straight up like, oh, the answer is the y-intercept. But again, I'll show you. We're going to do equations 1 and 3. So here's the problem. The reason you can't really do 3, like setting them equal to each other, is because 3 is an x equation. So this is a scenario, right? So 3 is x equals 0. So if I set equation 1 like this, then I just say 103 minus 5 times 0, y equals 103, right? So x equals 0, y equals 103, 0, 103. Do not set an x equation equal to a y equation because they're not the same letter, okay? So that's one that students will often overlook. They get so trapped into the methodology, which is, it happens, that you kind of ignore that fact, okay? So we have all of them now. So then step 10 is to calculate objective value. For max/min. So I just plug in these numbers. So C is equal to 9 cents times 35.2 ounces of chicken plus no grain, right? And so my cost is going to be equal to $3.17. Like that's how much it's going to cost me to make this food, according to my analysis. For this one, now, if we do all chicken, we expect that to be the most expensive one. So we would expect this one to be cheaper because we're using grain, and grain is a lot cheaper than chicken. So if we plug this into our calculator, we're going to get $1.27 to make this food, this bag of food. Not too bad, much cheaper than all chicken. And then you do the all grain case. So this is basically looking at the extremes. You're going to use no chicken. And you're going to use all grain. And so you end up getting it's $1.03, right? So the all grain case is the cheapest. So this is the minimum. So the final analysis is that the cheapest way of making this food to meet all the nutritional requirements is to use grain, right? So 0,103 is the optimal solution to minimize cost down to $103. So 103 grams of grain. Now, in practice, would a company do this? Probably not, because, you know, again, there might be certain guidelines, like you have to have this number of like some kind of protein that's meat-based or something like that. But then again, there could be ones where that are only grain and no meat. Maybe the pet doesn't do well with meat, so it has to be grain, or vice versa, right? It has to be only meat and no grain because it, you know, the pet responds better to it. So those are things to always consider. But this is kind of an interesting problem in that in every case beforehand, the optimal solution was always in like that little boxed region, right? Right here, boxed region. And then the one before that, it was in the boxed region. And like I said, that's the first place I would always guess. But in the context of this problem, it was not. It was actually the open region. So kind of a different idea of seeing different problems. But that is linear programming in a whole. Just understanding kind of what you're solving for and being able to set up this nice table and solve equations, you know, in a step-by-step fashion, and keeping things organized will lead to success in the long term, just because when you start getting very, like, you know, sloppy, things start to fly everywhere and it's kind of hard to read. So that's pretty much it for linear programming.